the previous recording we discussed what the gravitational force is. We said that the surface of a planet, the gravitational force on any object at the surface of that planet, due to that planet, is going to be given by this expression. The gravitational force is going to be equal to the mass of the object times g, the value of the gravitational field at the surface of that planet. G depends on the planet, and m depends on the object, how much mass does it have. Now, that's the gravitational force at the surface of a planet. But in general, whenever we have any two masses, no matter where they are in the universe, they are going to exert a gravitational force on each other. That gravitational force is given by this expression. Remember, this is supposed to say RB, which is a constant, a very tiny constant, that we call a universal gravitational constant. Actually, just one note here, small g is not a constant. It is approximately 9.8 meters per second squared downwards at sea level at the surface of the Earth. But it is about 1.6 meters per second squared downwards at the surface of the Moon. So it is a different value. It's going to be a little less than 9.8 meters per second squared in Colorado, for example, in Boulder, Colorado. Now, however, this g here is constant. It's a universal constant. It's the same constant we will use no matter where we are in the universe. And the bottom line is, whenever I have two masses, they're going to exert a force on each other. It's going to be a tiny force. That's because the constant is tiny. And the mass of the first object times the mass of the second object, essentially the product of their masses, divided by the distance separating them squared. Okay, we are going to try to probe this a little further. Let's start with this. What about if we have, okay, let's read the question. What gravitational force would a 100 kilogram football player experience from the Earth? Now first, just as a reminder, in a question like this, when they give us 100 kilogram has the units of kilograms, which is the units of a mass. So the 100 kilograms refers to the mass of the football player in this case. So we know the mass is 100 kilograms. And we know we are being asked to find the gravitational force at the surface of the Earth. So that's easy. We just use this. Fg is going to be equal to 100 kilograms times minus 10 meters per second squared. The minus is to represent the direction that we have here. It's in the downward direction, so it should be minus. And Fg comes out to be minus 1,000 newtons. The minus again tells us of the direction, tells us that F sub g is downwards. Okay? Now, we'll try to probe this a little more. The question now is asking us, what would the football player experience from an equal mass player standing 1 meter away from him? Okay? So what we have here, two football players, a meter away from each other, and each one of them having a mass of 100 kilograms. What force would they exert on each other? Now, to do that, we are going to use this expression. We don't have the Earth involved anymore. We are talking of any two masses. Okay, so when we do that, so let's use the formula. It's G, which is given to us here, 6.67 10 to the minus 11. I'm going to do an approximate calculation here, just to give us a bulk figure. I'm going to approximate that to 7 10 to the minus 11 Newton meter squared per kilogram squared. Or what the heck, let me calculate it precisely. A thought crossed my mind that some of you might want me to calculate it precisely. So that's why I'm going to do it right now. 6.7 10 to the minus 11 Newton meter squared per kilogram squared. Now times the mass of the first football player, which is 100 kilogram, times the mass of the other football player, which is another 100 kilogram, over 1 meter squared. Now, okay, let's calculate these. 100 times 100 is 10,000. 1 squared is 1. So 10,000 over 1, so it's 10,000. So this is 6.67 10 to the minus 11 Newton meter squared over kilogram squared times 10,000 kilogram squared over 1 meter squared. You notice here the meter squared is going to cancel with this one, the kilogram squared is going to cancel with this one, and we are left with newtons. And we have 6.67 10 to the minus 11 times 10,000 over 1. So that comes out to be 6.67 10 to the minus 11 plus 4. That's what we have here. So 10 to the minus 7 newtons. That's our F. 10 to the minus 7 newtons is very tiny. It's about a millionth of a newton. Compare it to this, where we are talking of 1,000 newtons. A millionth of and a thousandth. So the force that the Earth exerts on the football player is 1 billion times as large as the force that the other football player exerts on him. Okay? Now 1 billion, that's because this is 1,000 and the other one is 1 million. So 1,000 millions is 1 billion. Okay. So this force is very tiny. Since it's about 1 billionth the force that the Earth is going to exert on him, actually we are not going to feel the effect of that force. It's not going to affect most of what we do. It's a very tiny force. Now, what about the big picture? What's going on here? Now we said whenever we have someone on Earth, let's call that someone an Earthling, they are going to experience this gravitational force. But then we also said that any two masses are going to exert a force on each other that's given by, let me go back a few screens, by this expression. Now, what if we apply that force to people on Earth? I mean, we apply that expression to the Earth and the people on Earth. Can we find the gravitational force that the Earth exerts on Earthlings by using that same expression? Okay, I'll go back to this slide, but I'll skip here for a second. So this is what we are talking about. Can we think of every object on the Earth as a mass, and the Earth as a mass, the blue big mass? What force are they going to exert on each other? Now, what we are saying, F is G M blue M red over D squared. It's a universal gravitational law. We should be able to apply it here as well. Now, so if we are going to apply it, consider the sizes. M blue is going to be the mass of the Earth. M red is going to be the mass of whoever is on top of the Earth, mass of Earthling. Now, what about the separation between the Earth and that Earthling? You usually measure distances from center to center. So that's the average separation. For example, this end of the Earth is much farther away than this end of the Earth, but the average position of the Earth is at the center. So we measure from center to center. Now notice, here it's a small diagram. In real life, it's even more prominent. This is very tiny compared to this, which means this D here is not really much different than the radius of the Earth. Okay, now if we apply that, this is what we have then. The force that the Earth exerts on an Earthling is going to be G, the mass of the Earth, the mass of the Earthling, the distance separating them squared. And the distance separating them squared is the radius of the Earth squared. So this is what we get. But since it's the same gravitational force as the gravitational force we talk about here, that force should be equal to this. And what's this? What's this M? It's the mass of the Earthling. So what we are going to do is, in this equation here, we try to isolate this a little bit, kind of to move it around. So it's just the same expression. See, we have everything. I just moved M Earthling out of the ratio. Once we do that, what do we notice? We notice that this equation can look like this thing times M Earthling. This thing times M Earthling. What's that thing? It reminds us of M times G, or G times M, which is exactly what we have. G Earth times the mass of the Earthling. What does this say? It gives us an expression for G at the surface of the Earth, what I have on this circle. Okay? So if we look at it, so what this gives us is G at the surface of the planet. It is big G, mass of the planet, radius of the planet squared. Now, that's why we say G is not constant. Because actually we measure R from the center of the planet to where the object is. That's why, if this is the Earth, and we are here on top of the Himalayas, the distance to the center of the Earth is going to be different from if we were at sea level. So for that reason, G at the top of the Himalayas is going to be a little different. Actually, it's even a little bit more involved than that. Think about it. What if we are at the surface of the Earth and I have a skyscraper, for example, here, a big building, and I'm at the bottom here of the building. So what's going to happen? The mass of the skyscraper is going to be above me. If it is above me, what is it going to do? It's going to try to pull me upwards. So actually, the minute I walk into that building, if I compare the weight that I will experience, or the gravitational force that I will experience, is going to be different inside a skyscraper with all the huge mass that it has on top than if I was away from any skyscraper. Okay? So again, just a couple of things. G is not simply an acceleration, even though it has units of acceleration. It's a measure of the gravitational field strength at a particular location. It's not constant. It depends on the location on a planet, and it depends on the planet, and it is given by this.